Hi, this is part 2 of my video on using HF amateur radio transceivers from the mid-1970s. In part 1 I talked about how to set the frequency and read it on the front and some of the theory of operation. I'm now going to talk about how to actually set the thing up to transmit. As I said in part 1, this type of transceiver was made by a lot of different companies, but the one we're going to look at is the Yaesu FT101b from 1975-1976. In the early days of radio, hams would have two separate boxes, one with a receiver, one with a transmitter. But that's quite wasteful of parts because you end up duplicating a lot of bits inside the two units. With a transceiver, with some clever switching, you can make use of a lot of the same bits simply by rerouting the signals round inside. Okay, so let's see what's happening when the transceiver is switched to transmit. I'm showing a voice modulation, but of course it could be other forms of modulation. So we have a microphone here now that's feeding a signal into that mixer. Originally that mixer was the other way around, if you remember, and it was feeding audio out to the loudspeaker. That mixer mixes it with the 3.18 megahertz oscillator to produce our IF frequency. And this is a IF amplifier that boosts the signal up. It's also got a filter in it which basically removes everything apart from the bit we want to actually transmit. This arrangement is exactly the same as it was on receive. So we're mixing the VFO, which only has a range of 500 kilohertz, with a heterodyne oscillator so that we can cover the full 1.8 to 30 megahertz range of this transceiver. That is filtered to remove the sum, I think it was, of these two, what we don't want, to leave a signal of around 5-6 megahertz. That's mixed, so now what's coming out here is the frequency that we actually want to transmit on. And that goes through the pre-selector, which once again is working backwards now, to remove anything that we don't want from this mix, and just leave the bit we want to transmit. That's then fed to the power amplifier, which in the case of this transceiver uses valves, of course. And then we need a matching network because the valve amplifiers have very high impedance outputs, and the antenna system, as I'll talk about in a moment, only has a 50 ohm output. So we need some kind of matching network, and there are two controls on the front, plate and load, which are going to deal with that. In the early days of radio, radio hams would simply string a piece of wire between something like a tree and the side of their house, which was insulated from both, and run the cable from that straight down into the transmitter, and then might be an earth stake or a piece of wire laid along the ground. So the impedance of this antenna system was pretty well unknown. You could try and make some kind of calculation, but generally they had a matching network, and they just measured the current that was going into the aerial to figure out when the transmitter was working at its most efficient. If you wanted to find out how much power you were transmitting, you just measured the DC input that you were feeding to the final stage of the transmitter. And in fact, if you look at the manual for this rig, they're still doing the same thing here. They're talking about this having a DC input power of 180 watts. That's not what it actually transmits. So what was wrong with that? Well, one of the problems is if you don't happen to have a radio room which is right next to your antenna, then this becomes extremely difficult to arrange. And what you really want is some form of cable that you can feed the transmitter to the antenna system at a fixed value of impedance. Now, there are various methods of doing that. If you have a balanced antenna, that is a dipole type antenna where you have two parts, two separate pieces, and this is what we call a balanced antenna because neither part is ground. This system here is called an unbalanced antenna, because one half of it is grounded and this bit is live. So if you had this type of antenna, then it can have a characteristic impedance of around 600 ohms, and you need a way of feeding that. And it just so happens that if you take two pieces of wire and you space them about an inch apart, you get a 600 ohm cable, and that type of cable was called ladder line. And you can sort of see why, because here are the two wires, here and here, and in between there's a plastic piece of insulation to maintain that 1 inch spacing, and you can see why it's called ladder line, because it looks a bit like a ladder. Now that's great, but you can't put that ladder line close to any walls or anything. It needs to be spaced away from something. You can't just sort of run it through a small hole. Whereas this type of system with an unbalanced feeder, you can always use a network at the bottom of the antenna to convert the unbalanced to a balanced system, and the device for that is called a balanced to unbalanced. If you do that, you can then use the type of cable that you're probably familiar with called coaxial cable, where you have an outer sheath which screens the cable and an inner conductor and some insulation that spaces the two apart. Now, this type of cable has a much lower impedance, and it was also used for audio use, for if you wanted to connect a microphone to an audio amplifier, for instance, to, I don't know, for a microphone to record instruments in an orchestra, where you'd need lengths of connecting cable that was screened. So there were a couple of impedances of this stuff. One was 75 ohms, which was used a lot in the audio industry, music industry. And later on, because certain types of vertical antenna have a characteristic impedance which is much closer to 50 ohms, 50 ohms became the standard. And in fact, on this radio, 50 ohms is what it's designed to work with. On the earlier radios, some of the KW ones, it was still 75 ohms. Okay, now to connect these cables to the various things, there are a variety of different connectors. There's a heck of a lot of them actually, but here's some of the simple ones. This is what's called an N-type connector, and as you can see, it's double screened. This is very good for very high frequency work. The next large size connector is the PL259, which is sort of like a big pin inside a screw-on connector, which you just screw the two things together. And then you've got on the smaller side the BNC connector, which is a bayonet fitting that just pushes on and twists. Very easy to connect and disconnect, but not such a good connector from the point of view of losses, but certainly perfectly adequate for lower powers, and it certainly would work fine from this rig. Now, you can obviously get adapters to adapt from one thing to another, and this particular one, as you can see, adapts N-type to BNC. This one does N-type to PL259, which is this type. So you can easily adapt one thing to another depending on what cables you're using. Generally, adapters at very high frequencies do lose signal, but at these sort of frequencies we're talking about, that's really not going to be a problem. When we want to set this radio up to transmit, we're going to need dummy load, and it needs to be a 50 ohm dummy load. Now, a dummy load is basically a resistor with some cooling fins on it that's capable of taking a reasonable amount of output power. This is a 60 watt one, 50 ohms, and as you can see, it's got an N-type connector, so we'll be needing one of those adapters. As I talked about earlier, if you want to feed into an antenna, you're going to need a system to match the impedance of the antenna to the 50 ohm output of the rig. And this is an ATU, this one's made by MFJ, and this actually has a setting on it to dummy load. So this actually has a dummy load built into it, so if you have something like this you don't need an external dummy load. And it's also got a meter that allows us to measure the input power and the reflected power. That happens when the antenna is not matched to 50 ohms, called VSWR. Now the radio actually has a power meter built into it, and if we switch this switch up to PO, power output, we can see that there is actually a scale on here to show us an idea of the power output. Unfortunately, you also, with this type of valve amplifier, need to make sure you're not overrunning the valves. And this is the cathode current, I for current and C for cathode. And you really don't want this to exceed 200 milliamps because the valves in here would be burnt up, would be destroyed if you overrun them. So I like to have a separate meter to measure the power output while I'm tuning up, so I can leave that set to IC and make sure the current never goes beyond about 300 milliamps. Now the antenna matching unit I showed you earlier has metering on it, but not all of them do. This is one that has no metering on it. So you would need a separate SWR and power meter, and they come in various forms. Some of them have two separate meters, one for forward, one for reflected. That's the power going into the aerial and what comes back because it's not properly matched. And some just have a single meter and you have to switch between them. Okay, so let's connect all this together. So here's my dummy load. That's connected by a piece of wire to my power meter, and the connection marked aerial or antenna. The side marked transmitter, that's running through a piece of coax to the rear socket on the radio, which is marked antenna or ant. Right, here we are. I've switched the thing on. Now I've also switched the heaters on this time because we weren't actually going to transmit now. The valves on this are only used for the transmitter power amplifier, so if you just want to receive, you can turn the valve heaters off and prolong the life of the valves. But when you switch this on, you need to leave it a couple of minutes just to make sure the valves are fully warmed up. So what do we need to do? Well, first of all, we need to set the frequency we're going to use. So let's choose, let's say, the 80 meter band. We're on the red scale, and let's choose a frequency of 3.65. So I've got my 3.65 on there. Let's turn the volume up, and now I turn the pre-selector to maximize the noise. I set the plate to the 80 meter position, and I'm going to set the load to around about 1. Okay, the next thing I have to do is put the mode into tune, because we're going to tune the thing up. I've got this set to IC for the cathode current of the valves. I'm going to switch my power meter to the 20 watt setting because I don't need a lot of power to tune this thing up. Okay, when I click this switch, I need to make sure that the mic gain and the carrier over here are down at 0 and the clarifier is off. So now I'm going to switch MOX on, and when I do that, it is now transmitting, but the carrier is turned right down, and you can see there's a tiny reading on the meter there. So now what we do is to slightly increase the carrier, which is the outer one of these two knobs, and as I turn that up, you'll notice that the anode current is changing, cathode current is changing here, but also now we're getting a reading on this meter. So I can now peak this up using the plate control to get a maximum value on this meter here, and also the pre-selector control, and I can adjust the load, and you notice actually the load seems to be maximum 0. That'll depend on your particular radio. So let's just turn that to get the maximum, and as I say, we've only got 100 milliamps. If I turn up the carrier, you'll see the power goes up and also the collector current. So that is now tuned up for the 80 meter band. So let's switch that off. Let's choose a different band. Let's say the 20 meter band. Again, if we want 21 meters, we're now on the black scale, so that's 14.1 megahertz. So let's do the same thing. Let's turn this plate control till it points to the 20 position, because that's what we're set to, 20 meters. Let's turn the pre-selector control till it points to 20. We'll put the load back on 1 again. So let's turn up our receive gain and find the point at which we get the most noise, which is there, and turn that back down again now. Now let's switch the transmitter on. Once again, we've got the very small reading for the quiescent current, and let's turn the power up now. And once again, you notice that we're already getting a reading on the power meter here. Again, if you switch this to power meter, you can see that you could do that, but you can't look at both of those things at the same time. So let's just peak that value up and also adjust the plate. And the load, and now you notice that the load is actually peaking on about 1. Let's turn the power up a little bit. Now the controls are very sensitive as you increase in frequency, and you'll notice that I only have to sort of breathe on the controls and things change. That's quite normal, and if you distune this, you'll notice you get absolutely nothing out. So probably if it was actually pointing to the 20 on here, you wouldn't have seen anything. But because we peaked it up on receive to get the most noise, you actually had a power reading when we turn this up. So that's tuned up for that particular band now. Right, okay, so let's switch that off again. Now, you don't want to leave it too long in the MOX position because the transmitter is running continuously. If you were using voice in single sideband mode, then of course it would only be producing power on the peaks of your voice, so it's only effectively on for half the time. When you're in this tuning mode, you're on the whole time, so you really need to limit how long you leave this switched on for. So that's basically set this up for producing signal at that particular frequency. The next thing you would need to do was connect it to your antenna system. If your antenna system was a 50 ohm one, then you wouldn't need really to adjust anything else. If it's a random piece of wire, then you would need to use the ATU to actually peak that up, but at least you know that the transmitter is running at 50 ohms. The same thing applies when you're adjusting for signal. Obviously choose a frequency that somebody isn't talking on, and switch this on a lower power setting with your metering set for a lower power, so that you don't overrun the transmitter with a very badly matched antenna. Because if the antenna is matched, then the power is being fed back into the radio and it's cooking it. What you want is all the power to be going to the antenna and being transmitted. Now, if you were going to use a separate aerial matching unit like this one here, for instance, you would need a way of switching between the dummy load and the aerial if you want to use different bands and switch between them. And you can get something like this, which is a coaxial switching system. This one has 3 positions, so you could select the dummy load on one and one antenna system there and perhaps a different antenna system there. That makes for a lot of wiring. You need a lot of patch leads to connect all this lot together. The advantage of a unit like this is that you can switch to dummy load. Bypass means it doesn't have any of the tuning in it. And then when you peak the transmitter up, you can simply switch back to an antenna position and then adjust the aerial matching to match the antenna system to the rig without all those wires and switches and things. So it is quite a lot easier with a unit like this than it would be with the separate part. Well, I hope that's given you some ideas of how to use one of these radios. They're not the easiest thing to use, but very rewarding to put something of this age on the air. And they work perfectly fine. In fact, to some extent, the receivers are better than modern rigs because they actually have a tuning system, so you can get rid of some of the out-of-band signals. Although they lack some of the modern features of up-to-date radios.